Hello everyone, this is Sarah Wu from the Department of Chemical and Biological Engineering at the University of Idaho. In this presentation, I'm going to introduce our study on producing a green nitrogen fertilizer from air and water by a novel electric discharge process. The long-term goal of this project is to reduce our reliance on fossil fuels and associated environmental issues, such as greenhouse gas emissions, by developing a green technology to efficiently manufacture nitrogen fertilizers using only air and water as substrate, operating at room temperature with no need of catalysts. And I'm glad to take this opportunity and share with you our early stage progress. Well, as you know, the abundance of nitrogen gas is existing in the ambient air, but the plants can only live on fixed nitrogen in the form of ammonia or nitrogen oxides, including nitrogen and nitrate and nitrite, which are the major components that the nitrogen fertilizers have to offer. Basically, three major nitrogen fixation processes for producing ammonia and nitrogen oxide. Lightning and microbial conversions are two major natural ones, which cannot well controlled for mass production of nitrogen fertilizers because of the inefficient conversion and low producibility. The Haber-Bosch process is one of the greatest scientific achievements in the 20th century, which allowed an industrial-scale nitrogen fixation for agricultural production. However, both the Haber-Bosch process to convert nitrogen to ammonia with hydrogen, fossil fuel-based hydrogen gas, and the Ostwald further oxidized the ammonia to nitrogen oxide require a substantial industrial infrastructure that consumes massive amounts of energy to provide high temperature, high pressure catalytic conditions, and also creates great volumes of carbon dioxide and other pollutants. Therefore, there has been a growing interest in alternative, greener methods that move away from the centralized fertilizer production. While looking at the very few alternative routes, including biological and electrolysis, electric discharge is the most direct nitrogen fixation route. Both oxidation and reduction routes of the nitrogen fixation can be induced by the plasma discharge of air above or directly in water without catalysts or any external source of fossil fuel-based nitrogen or hydrogen based on these ionization reactions shown here. So nitrogen gas can be ionized to form the nitrogen radicals, while hydrogen radicals can be produced from ionization of water. And further combination of the radicals from nitrogen oxides without needing to go through the formation of ammonia, while the ammonia can also be synthesized with the available nitrogen and hydrogen radicals. Well, these reactions look very straightforward, right? But much more challenging is to activate these reactions by electric discharge in water and air, as well as engineering of this process for simple operation and better control. By now, the research about liquid phase plasma is mostly for water and wastewater treatment, and its application is very limited due to very low concentrations of reactive species are collected in water. Also, several problems to solved in engineering. For example, pulse power is not easily available. And second, the long-term stable plasma generation in water is very hard to achieve. And third is about the reactor design. All the existing research is using a batch type reactor, and it's almost impossible for the local discharge at the electrodes, because you need electrodes to discharge. It's hard to achieve effective and uniform treatment for the whole batch, as you can imagine. The concentration of fixed nitrogen species is too low to be used as a fertilizer product. So the goal of our research is to find a solution for these challenges by designing and evaluating a novel continuous flow liquid plasma reactor, which is also, you could call it electric discharge reactor. This reactor is not dependent on pulse power and can also use a AC power supply, which is available everywhere, to create stable discharge in both water and organic solutions. And we also designed the reactor into a continuous process. So the treatment is easy and fast. Operation is simple. This work could be a big breakthrough for liquid plasma application, based on which unlimited applicable technologies can also be developed based on the properties of liquid plasma. It can be used for killing bacteria. It can be used for degradation of organic compounds, for environmental remediation, and also for chemical synthesis like the nitrate and nitrogen fixation, and synthesis of polymer plus the natural nanomaterials, as well as the biomedical applications. So the bottom left here is our reactor design. As compared to pin-to-pin and pin-to-plate type of discharge in the typical batch mode reactor, to use a pulse power for frequent exciting of the electrons, which is not stable. In our reactor, the discharge point has moved from the electrodes to a center opening, where the continuity of the discharge current was achieved through the moving of the liquid in the form of a displacement current in the plasma phase. So this structure actually ensures complete treatment for anything that goes through. Experimental setup is on the right. Basically, you need a pump for water flow and a high voltage transformer with one plasma reactor like this. One stable discharge generated in the liquid passing the discharging zone, intensive treatment will be available. So for treatment of liquids, the operation mode can be either continuous passing the liquid through the reactor with a certain flow rate, for which we tested one pass and two pass. Two pass just means is passing everything through twice. Or another option is to circulate certain volume of liquid in the system again and again for a certain time, which we call a circulation mode. So in this preliminary study, we use the nitrogen oxide concentration, NOx, which means the sum of nitrite and nitrate in the plasma treated water, to evaluate this discharge process. And our objective include the study of the effect water flow rate and air flow rate for the production of nitrogen oxides, as well as nitrogen oxide production with one pass, two pass as compared with the circular mode of operation. The results of nitrogen oxides concentration, NOx, in the treated water by 1 and 2 passes with the water flow rate of 50, 100, and 200 mL per minute are shown in this column chart. We can see that for each level of water flow rate, nitrogen oxide concentration for 2 pass is higher than 1 pass, of course, but not twice as much. So the energy efficiency for 2 pass is lower than 1 pass. Lower water flow rate resulted in higher concentration using lower power consumption. So seems like the lower water flow rate is a better choice for improving energy efficiency. Similarly, there is an effect of airflow rate on NOx production is evaluated with the NOx concentration at an airflow rate of 1, 2, and 3 standard liter per minute with the same water flow rate by 1 and 2 pass. It was found that the higher airflow rate resulted in a higher NOx production with lower power consumption. NOx concentration for 2 pass is higher than 1 pass, but not twice as much again. So it seems that using a higher airflow rate is a good way to improve energy efficiency for continuous passing type of operation. But as you can see, the concentration of NOx by 2 fast only reaches up to like 300 milligrams per liter, and seems like more passes won't increase the concentration much more. But what if we need to make a more concentrated fertilizer? A circulation mode of operation by water running again and again in a plasma treating system would be a good choice if only one reactor is used. By operating in a circulation mode for 4 hours and water flow rate at 100 mils per minute, we found that nitrogen nitrate production keep increasing to a concentration reaching 1,000 milligrams per liter, and show the potential for further increase with longer treatment time or improved operational conditions. At the same time, conductivity increased all the way up to 4,500 Siemens per meter, and pH decreased dramatically in the first hour to around 3 due to the production of hydrogen ions with the NOx ions. We do see that the production of hydrogen peroxide increased up until like 90 minutes before it dropped. High concentration of hydrogen peroxide production indicates highly oxidative species, which means this treated solution could be possibly used as a green disinfectant, pesticide, or fungicide at the same time as a fertilizer. So with these promising preliminary results, the feasibility of efficient and effective nitrogen fixation by our continuous electric discharge process has been proved. To develop it into a viable technology, the next step is that we have to improve the nitrogen oxide concentration by optimizing operational conditions and the parameters, and also achieve a higher energy efficiency, applying a heterogeneous catalyst for higher production rate. Furthermore, to design prototype or work on the scale up of the process for the next level. Finally, we want to acknowledge the support of USDA NIFA for this project. And authors also would like to thank University of Idaho Summer Undergraduate Research Fellowship Program and the College of Engineering Grand Challenge Scholars Program for supporting undergraduate research in this work. We will be very happy to answer any questions you have. Thank you for your attention. Have a wonderful day.